So our next speaker in today's afternoon session, Professor Marcus Huber, who is very well known to the audience here, so perhaps needs no introduction, but still let me mention that he is at the QIQT23 Vienna and is one of the leading experts on the interplay between quantum information, quantum thermodynamics, and has been making outstanding contributions over many years on the interplay between quantum information and experimental implementations, especially using quantum photonics. So today he will be speaking about quantum thermodynamics, and it's a very interesting topic. Analyzing quantum measurements through the lens of quantum thermodynamics. So we look forward to hearing Marcus. Welcome, Marcus. Please start.
Yes, thank you very much for the kind invitation and the kind introduction. Can you hear me well?
Yes, yes. And you have 45 minutes, Marcus. And so, and then we'll have the question answer.
Wonderful. I think I might even be a slight bit faster and have some more time for discussion if needed.
Okay, okay. So, no rush.
Okay. Okay. So I thought I'd talk a little bit about our recent efforts into the thermodynamics of quantum measurements. And this is work done by a whole lot of people in and around my group. And yeah, let's just re-examine for a second. I mean, we all know textbook quantum mechanics, or most of us, I assume. And there is this whole philosophical debate about the measurement that I do not want to get into too deeply. But in essence, what is always there is the fact that the description of a measurement is always with this divide into there's a quantum system that comes, then it enters this mysterious classical measurement apparatus that at some point displays one of many possible measurement outcomes I. And upon seeing that classical outcome, the post-measurement state is projected into one of these states, which is basically like this EI on the right-hand side. Conventionally, they are just projectors onto one-dimensional subspaces. So you just get a pure state with a certain probability, and the probability is exactly just the overlap of the projector with the state. And this is all good, and from an operational perspective, and this is why, I mean, despite a century of debates about the interpretation, it works really well, right? I mean, we can approximate these things pretty well, but also working in a photonics lab, I also noticed, of course, we cannot actually do this. I mean, these non-demolition measurements are really hard to do, and even then we don't get exact pure states out. And it's also a good thing, because if you think about the thermodynamics of the process, it becomes a little bit mysterious. And I want to illustrate it along the three laws of thermodynamics that are actually not as settled in a quantum case as one would want them to be. But say the first law says something like the energy is conserved and a change in energy can always be attributed to a change in work plus a change in heat. But then how does this square with this measurement postulate? For instance, what does it mean to measure a superposition of two different energies? Does it mean that the measurement apparatus essentially always has to compensate for the inevitable energy change upon collapsing such a superposition in the energy eigenbasis? And the thing is, the axioms of quantum mechanics, they don't actually tell us if we take them at face value, because it's just an element of the theory that this projection happens, but not what the classical apparatus does in the process. But of course, one could say, okay, I really deeply care about the first law, so let all the energy change of the system be exactly compensated by the measurement apparatus. This is not derived from first principles, but it's something one could say. For the second law, something very similar happens. The output state of such a projection postulate, say, I measure in any projective measurement, my output state is pure, while after the measurement, my system has entropy 0. If it was a mixed state before, it had a larger entropy than 0, then of course, the entropy decreases. That doesn't necessarily violate the second law because it's not a closed system. But then if we believe the second law, and many people have lost bets against the second law, we'll have to concede that the measurement apparatus will somehow have to compensate for the decrease in entropy of the system by respectively increasing its own entropy, because otherwise we would violate it. But the third law, depending on which formulation you take, could be formulated as the entropy approaches zero, or as I try to reduce the entropy of a system, or even drive a system into a pure state, the resources required for this process diverge, so they go to infinity. So there are many variants of this. So basically, to actually cool to the exact ground state, I need to invest an infinite amount of work, or in Landau erasure, to actually perfectly erase a bit, I need to invest an infinite amount of time. And there are whole debates about what are the resources and when is it valid. But nonetheless, if my projection postulate is able to output pure states, well, it will have to compensate for the resource, which is no longer as easy as it was for the first two laws, because somehow it's easy to say, well, my measurement apparatus has a finite energy compensation, a finite entropy compensation. But now this is really divergent. So we can't just say, oh, it just uses an infinity amount of work. So that's what prompted us to look a bit more deeply into measurements. But how could you possibly even model measurements in a self-contained fashion? And in some parts of the foundations community, it was noticed, or some people do model measurements as really a physical interaction between a system and a measurement apparatus. But there are two approaches that I'd like to show on one slide here. One of them is a quantum system interacting with a pointer, where both of them are essentially quantum systems, where the pointer might be coarse-grained afterwards or might be a little bit larger. But this interaction is very controlled. So I have system and pointer initially uncorrelated. I have a USP, the system pointer unitary, like some interaction Hamiltonian inducing a unitary transformation that is controlled, and a system pointer state that basically correlates system and pointer. And then there is another approach that can be easily incorporated, which is to really include the entire environment and try to model the entire objectification of information, or the broadcasting of a quantum system. So not just how a pointer gets correlated, but how the entire environment agrees what the pointer state is. And this is often summarized with the word quantum Darwinism, where the idea is a little bit different, that essentially the pointer now interacts with all potential parts of the environment and naturally tends towards a state that is often called SBS, or spectrum broadcast structure, or is said to have spectrum broadcast structure, which is essentially meant to convey the idea that the information about the pointer state is now easily retrievable from any reasonable size fraction of the environment. Now, this can be framed mathematically by a couple of conditions. So for instance, for the system pointer correlations that we've worked on a couple of years ago, well, they need to be what we called faithful. What you see here, this just means that the sum of this I projection on system and I projection on pointer needs to be 1. It just means that whenever the system points I, the pointer, or when the system is in state I, the pointer also needs to point in the direction I. So there's no error. It should be unbiased in the sense that the probability of the pointer states is exactly reflects the probability of the initial system in that measurement basis. And it should be non-invasive, which is maybe a bit of a bad word, but anyway, we chose it back then, meaning non-invasive in the measurement basis. So if the state is in state I before the measurement and I measure in the basis, it should afterwards still be in that same state. Okay, and for this whole objectivity and quantum Darwinism, there are a lot of papers. I'm just showing this one here. But essentially, it is an addition to all of these three properties. We need correlations where essentially now each subpart of the environment needs to be in a state conditioned on the pointer state. And ideally, those environment states should be as orthogonal as possible, such that I can read off from any subpart of the environment the state of the pointer. And of course, if you look at it, actually this SPS structure it fulfills all these criteria, but has even further requirements. Okay, and then how could a measurement look like? Well, I could now model my measurement apparatus as a quantum state that basically does this. So for instance, I have a system, and usually if you look at literature, that system is for some reason in a pure state. The detector might also be in a pure state, and the environment is basically also in a pure state, ground state. So like the environment is just a couple of zeros. And then everything is easy. The pre-measurement step is essentially just a C0 gate, and this is everything. It's faithful, unbiased, and non-invasive in a sense, because now system and pointer are correlated perfectly. And you see, before I had a superposition A0 plus B1, now I have A00 plus B11, and now the pointer states perfectly reflect the system. It's all in the correlated subspace. And actually, if you look at Darwinism, you can also just think of it as a bunch of C0 gates applied between the pointer now and all the different sub-environments, and this will exactly lead to this SPS structure. And there are a couple of reviews. This idea is not entirely new, and it just means I'm not taking a stance here that this is the correct way. I'm just saying this would be a self-contained way of modeling quantum measurements in an entirely unitary fashion, which basically allows us to talk about the thermodynamics of the process. However, the thermodynamics here is a bit tough because it's in an environment of absolute zero, and pure states are everything that exists. However, our real environment isn't like this. In reality, we might have a mixed quantum state coming in. We usually have what is called event-ready detector. So we have some out of equilibrium system that is carefully chosen to essentially be ready to detect something in a particular basis. So it's usually something that is at a temperature. So this inverse temperature beta is larger than the environment temperature beta. So it's something that is basically cooled down and then driven out of equilibrium, and the entire environment is thermal. Now, to be a bit more concrete, what could this look like? So my system could be, for instance, say, a photon with mixed polarization state, flying along, single photon. And then the unitary connecting the detector and the system could just be a polarizing beam splitter that connects the path and the polarization degree of freedom, horizontal and vertical, go in two different directions. And now there are two such single photon detectors that can just tell photon or no photon. And those are usually, like here is a nanowire, those are usually systems driven close to a critical edge where a single quantum of energy can trigger a cascade into a new equilibrium. And of course, in the course of this cascade, that there will be an objectification of information. But let's talk about the pre-measurement, because already the pre-measurement has some interesting thermodynamic constraints. So first of all, the very fact that I have a non-zero, non-rank one state, i.e. a mixed state, means the first condition of faithfulness is not achievable, because what you're really seeing here is that the post-measurement state that should be unitarily obtained from the pre-measurement state should live only in this symmetric subspace, or in this very small subspace of I and I, in this correlated subspace. But of course, if I have too many eigenvalues, I just can't reduce the number of eigenvalues via unitary, and I can't all put it in this correlated subspace. So there must be errors. So there must be times when I come in with an H photon, but the V detector clicks and vice versa. But interestingly enough, statistically, we can prove that even though you have a full rank, you can preserve either unbiasedness or non-invasiveness. So either the post-measurement state is disturbed, or the statistics that you perceive on the detector does not reflect the correct statistics of the input state. And we thought that actually like focusing on unbiased is probably the more reasonable thing to do, because unless you use it for preparation, usually what you care about a measurement is actually to have the statistics correctly reproduced. And it's good that this is possible. But then what about the second step? That might even be more interesting. So now we have this imperfect correlation. So we have this detector that is now essentially correlated with the system, and in an unbiased fashion reflects the input statistics of my quantum state. How does it now interact with a thermal environment unitarily to reach a new equilibrium state, such that this new equilibrium state is of this spectrum broadcast structure? And that kind of goes very deeply into the quantum origin of the second law, because at first, how can the second law even be true? Like, if I have a unitary interaction, how does a system even relax? You would think, well, a unitary is essentially this constant path upon some orbit in the Bloch sphere. It's constantly in unitary motion, so to speak. It is also, it's reversible and all of these things. And yet, closed systems tend to equilibrate. And I can't do this entire field justice, but there are many approaches and explanations for this. The most popular ones being like this eigenstate formalization idea, where you say, well, of course the system keeps moving, of course it doesn't equilibrate, but reasonable physical observables that I can couple to this system would not be able to tell the difference between an equilibrated system or an out of equilibrium system, simply because the overlap of the interaction Hamiltonian, or the eigenstates of interacting many-body Hamiltonians, look very thermal to the eyes of reasonable physical observables. And then there's another idea, which is also often brought in conjunction, which is that of dynamical equilibration, where to say, okay, yes, I'm constantly moving through my big Hilbert space, I'm moving in an orbit, but from a local perspective, or from the perspective of reasonable observables, essentially, even though at some point my orbit is completed and I have a recurrence, this recurrence time is so astronomically pushed to infinity that I will never observe it. And actually, along this path, most of the time, essentially, I'm so entangled that my marginals are very mixed, or from the perspective of local observables, I'm just indistinguishable from thermal, that effectively, by averaging just over a tiny bit of time scale, all the rotation takes care of the off-diagonal elements, and I would end up in a new thermal equilibrium. And so the question that we had was, well, is this combinable? Could we combine a detector or a pointer with a thermal environment, leave it to interact naturally, and would then dynamical equilibration lead it towards such an objective or spectrum broadcast state? And that is the content of this paper, essentially, where, we have a central pointer system and a lot of environmental systems, and we ask, what are the conditions on the interaction Hamiltonian between the pointer and the environment, such that the natural time evolution of an initially uncorrelated pointer environment would, in the asymptotic limit, lead to this SPS structure? And we find, while this is not exactly possible, like the environment states can never be fully orthogonal, simply because these correlations, they would be of low rank, and of course, if the whole thing starts in full rank, we cannot end in low rank. But we can get to the fact that the fidelity of different environment states I and j, with the larger fractions you take, exponentially goes down. So effectively, they become something like effectively orthogonal. And we can essentially prove that the form that Hamiltonians need to take is such a non-surprising conditional form, i.e. the time evolution or the Hamiltonian that is seen by the environment needs to be conditioned on the state of the pointer, so that depending on the pointer state, you see a different evolution such that you get essentially distinguishable macro states of the entire thing. And this entire idea or framework has been often mentioned, and we just dub it again of the measurement equilibration hypothesis, i.e. the hypothesis that essentially quantum measurements are autonomously or self-containedly realizable via natural time evolution and equilibration and thermalization. And how would this look now from an energy level structure? Like, so for instance, I could have here on the left-hand side, I want to measure whether the system is in an excited state. And then what could the detector environment system look like? Well, it would need to be in a kind of a blocked out of equilibrium metastable state that is kind of alone here and cannot move around. But then the interaction with the system basically moves up the population into a huge degenerate subspace where now the population can move freely around and start thermalizing, because any self-contained unitary evolution, I mean, Hamiltonians are fundamentally time independent, and time-independent Hamiltonian evolutions only move in degenerate subspaces. And in this way, this would be just a, like, to get a bit of a more intuitive understanding of how this could look like and what could be going on here. Yeah, and which already brings me to my conclusion, which is that effectively, I think there's a rich interplay between thermodynamics at the quantum scale and the idea of measurement, but at the same time, turning it on its head, I think that we can't even say we have developed a genuine theory of quantum thermodynamics if we do not understand what measurements do. And before I go to these conclusions, let me just illustrate this with another example. Say, in classical thermodynamics, we usually just write down equations of state, irrespective of whether they are measured or not, because in the end, we don't care. Measurement doesn't factor into things. Say, if I observe a car, it doesn't really make a big difference for its momentum. I mean, sure, if I scatter some photons of a car in order to see where it is, I will change. These photons will have a back action and the momentum of the car will change, but in a negligible fashion. And at the same time, the energy use or the work use of my camera I'm using to capture it will be small compared to the work output of the engine. So for all intents and purposes, I can practically say these things are irrelevant. But if I now want to do thermodynamics of small systems, not the thermodynamic limit, but really mesoscopic or even microscopic quantum systems, well, then suddenly the very action changes the system and induces a work cost that is not only comparable, but usually orders of magnitude above the system energy scale. So this is why I feel, or I would posit, that we really need to understand the thermodynamics of measurements if we want to understand thermodynamics at the quantum scale. And what can we conclude for this prior discussion? Well, actually, for the first law of thermodynamics, well, it is kind of important for this formalization for moving only in degenerate subspaces. This is how it enters. But what it does to energy superpositions is something we haven't looked at. And it kind of really depends on what is your notion of observer inside such an environment. And the second law, of course, holds globally as before, right? I mean, it's a global unitary revolution, so no entropy change. But actually, of course, we see the entropy effectively changes from the perspective of outside observers, but what about inside observers? What about conditional states? How does the total entropy change from the perspective of one observer who sits in, say, or is defined by this part of the environment. And maybe most importantly, the third law really limits the correlations in the sense of faithfulness, unbiasedness, and non-invasiveness, i.e., without investing this infinite amount of work or time into preparing the detector, we cannot actually get a perfect textbook quantum measurement, which is the only solid conclusion that I think is completely independent of interpretation, which is that essentially the projection postulate, as it is written in textbooks, is a convenient fiction in the sense that it can never be reached, it can never be realized, but by investing a suitable amount of work, it can be approximated. And effectively, this is what we're doing in quantum information technologies, because there we don't care so much about the work cost. And yeah, sure, I mean, the energy usage of my nanowire detectors, of my APDs, it may be orders and orders of magnitude about the energy scale of a single photon, but it does its job reasonably well. And yes, I should thank the funders, but more importantly, the co-authors like Max Locke, Nico Fries, Tom Rivlin, who's working on this too, Manu Schwarzhans, Jelena Gurjanova, Felix Binder, and I forgot, Thiago de Barba should also get a photo here. He's also one of the collaborators who's been working a lot on this. And with this, I basically told you what I wanted to tell you.
Okay, so thank you, Marcus. Already we have plenty of time for discussions, and so the talk is now open to comments. Shomik, please coordinate.
Yeah, if the participants have any questions, they can unmute themselves and ask directly to the speaker.
Yes. So let me then first go ahead and ask if there is no one yet to ask any question. So Marcus, thank you for the stimulating talk where you have outlined the ideas, obviously not going into much details. So let me first get myself clear. So when you talk about the SBS structure of the environment, that's a crucial component of your talk. So there, the effective orthogonality, now to ensure effective orthogonality, that part you quickly touched upon.
Yes.
You spoke about certain conditions on the interaction Hamiltonian.
Yeah.
Can you just elaborate on that part?
Yeah,
because
wonderful.
How do you ensure because for emergence of SBS structure, as I understand, it is effective orthogonality, how it is ensured, and to what extent it is effective, how precisely it can be delineated. Means effectiveness means in what sense?
So should I share my screen again, or?
Yes. That.
So, okay. This was all on this slide here. So, of course, so one of the first things we noticed was that if you have now the is rho zero, which is essentially the pointer state, the post-measurement pointer state of a pre-measurement, whatever, and some initial environmental states, even if the environment now starts in temperature zero, an energy conserving unitary orbit. So you apply energy conserving unitaries, or you have any, so that's what we do. We apply e to the IHT, where h is a time independent Hamiltonian, to both sides. And then we get from this a rho of t that we time average via this integral. This is the typical approach to kind of dynamical equilibration. And even if the environment is in temperature zero, this dynamical equilibration state actually cannot reach perfect SBS, because it necessarily populates the wrong subspaces, and there's no way around this.
So it occurs even in zero temperature.
Even in zero temperature, and at higher temperature, it's just more pronounced. And at first we thought, wow, this is
zero
really...
temperature, it happens because of that.
Because of the energy conservation. I mean, there would be a unitary which perfectly correlates, like the C naught before.
Because you impose total unitary.
Exactly. But the unitaries are very limited to work only in the generate subspaces of the total. Okay. And so, yes. That means actually all the paths that the unitaries can take do not actually lead for an exact SPS structure, which at first we thought, no, maybe that's bad news for the entire program. Maybe that's bad news for quantum Darwinism even. But turns out that essentially no, because once you start grouping, as we do here on the right, once we start grouping a lot of environments, a lot of little environment Hilbert spaces, so we assume this tensor product structure of the environments, it's made up of many constituents, and once we start bunching them together, some number, NQ, and we compute the fidelity of two such conditional environment states, so rho IQ and rho JQ, then the fidelity between them will be upper bounded by e to the minus a constant that depends on the initial state and the temperature, but it's a constant effectively once you fix the starting conditions, and the number. So that means that as long as I look at large enough environment fractions, they essentially become fidelity zero, or in other words, they become effectively orthogonal.
So the effective orthogonality emerges when the fidelity, the way you defined it.
Exactly. And in that sense, we felt it was an operational way of talking about this, because it might have been unreasonable to expect, and even in quantum Darwinism, right, to say, well, we don't want every particle of the environment to perfectly reflect the system state. That's way too much to ask, right? Even if I'm now in my lab and my avalanche photodiode lets out this avalanche and this new equilibrium state, and it makes a noise, and my computer gets a signal, and my computer's display sends out lots of photons saying photon detected. Yes, then there's a lot of particles in my room that now basically carry this information, but not every air molecule has now perfectly noticed that a detection event has just taken place. But if I take any subset that basically is able to see the computer screen or hear the detector, then
the subset corresponds to the way you define the fidelity in a sense.
Yes, exactly.
Yes, so that definition may vary. So according to that definition, what you mean by effective term orthogonalization would also vary.
Yes, absolutely. Correct? But given that, okay, maybe we didn't prove this, but given that the fidelity exponentially converges to zero, I'm guessing most reasonable measures of orthogonality would also reasonably decay with size.
Okay, so that is the argument. Yeah. So that is the argument. So that's interesting. So then what is the status of the third law in this context? You once made a remark that even if we do this, the third law is problematic. In what sense?
The third law is really most problematic in preparing the detector, because the environment I can't reasonably expect to cool. And so if I go back to this picture, to the very first one, no, here. Where am I? Here. So like, because in the end, the objectification by this unitary dynamics, that needs to be conditional, and here the size rescues you. That effectively, you will not get your environment perfectly correlated with your system as a whole, but you'll get enough information about your system percolating through the environment that you get all of these nice properties. But the first thing, the pre-measurement, is actually also often the hard part, to really correlate the pointer in the basis you want to, and perfect correlation between two systems can only happen if the second system is already at temperature zero to start with. So really the third law limits the preparation of your pointer in a suitable detection ready state. And
in a suitable detection ready state, you mean that would be contingent upon the type of detector you have, or can be generic?
Exactly. I mean, in the end, okay, mathematically, it's quite easy to see, right? I mean, if I have a full rank detector state and any system state, a unitary can only perfectly correlate them. The detector is basically in a pure state. And if the detector is not in a pure state, I cannot have perfect correlations. That's a limit. And in that way, the third law enters via basically unless I'm already given a detector in a pure state, I need to cool it down to be closer to a pure state, because then the measurement will be better. But as I approach the pure state, the work cost diverges. This is on a formal mathematical level, but on a physical level, it's also what we see, right? I mean, how do we build detectors? We try to find, we need to find macroscopic instruments that are sensitive to a tiny quantum fluctuation. But that also means usually we don't want it to be at a very high temperature, because we want the natural thermal fluctuations to not trigger false detection events. So this is why these kind of nanowires or superconducting detectors are very good, because you cool them down, you bring them close to a critical point, close to a phase transition of something, such that a single quantum of light is sufficient to trigger this kind of phase transition, which is then macroscopically noticeable, which I guess is one particular technological manifestation of this rather fundamental thing, that essentially you'd want the pointer to be as pure as possible. Or even in the example of a beam splitter splitting my photon into two paths, I want these two paths to not already be occupied, because otherwise I wouldn't be able to tell whether, like, if I now see photons in both paths, what does this mean for the polarization of the photon I was interested in? So you want the electromagnetic field in these two paths to be empty. Only then can the polarizing beam splitter actually work as a pre-measurement apparatus.
That's a good point. Yeah.
And which is fortuitous, because actually an optical photon at room temperature almost doesn't exist. So it's actually effectively very low temperature, because if we look at a single photon at like terahertz, and we look at the number of optical photons at 300 Kelvin, I mean, our rooms would be very dark if not for artificial lightings or the sun. So in some sense, temperature always has to be seen with respect to the energy scale we're interested in. But what we always need are pure states somewhere. And if we don't have them naturally, we need to create them. And that is limited by the third law.
So that is where the third law plays.
Yeah.
That's nicely explained. Thanks, Marcus. But I appreciate your remark that understanding of quantum thermodynamics is contingent upon understanding thermodynamics of measurement. And then thermodynamics of measurement, this third law is a critical role to play, which is not yet clear. Okay.
Yes, so we need to better understand thermodynamic laws and at the same time measurements, because otherwise, what can we really say about the efficiency of quantum engines or other things if we don't even know what it takes to observe them?
So when you said that statement, that is another provocative statement. So efficiency of an engine, then what it means to observe them. Can you explain it a bit?
Well, I mean, so the question is, if the effect or the provocative statement would be, if the effect of a quantum machine would be noticeable, it would also constitute a measurement. But if you want a noticeable effect, so like, I'm often wondering this, for instance, say you derive a model with a time-dependent Hamiltonian of a certain quantum engine with a certain efficiency. I mean, I'm not saying this is bad, I'm saying this is certainly very interesting, but the big question is, what would it take to actually observe such an engine in action? And also, maybe on the other hand, connected to all of this and the laws, what would be the cost of controlling? What's the cost of creating such a time-dependent Hamiltonian? Because I usually think about it, time-dependent Hamiltonians in the lab, I would create via shooting a laser or turning on a huge magnet that makes a macroscopic magnetic field that basically changes the energy spacings of some quantum system. But if I take this into the consideration when computing the efficiency, then the efficiency is usually around, I don't know, 10 to the minus 20, 10 to the minus 30, or even very negative, actually, in most cases, because I spend much more in the control than I get out of it at the end. But of course, there are other tasks, like in cooling, I don't care, right? I mean, might be really inefficient, but who cares if my goal is to cool and not to do so efficiently? Or if an engine is autonomous, if it's not driven by a time-dependent Hamiltonian, then may well output some useful work. But again, I'm just saying, I think there are a lot of really fundamental unresolved questions at the interface of quantum information and quantum thermodynamics. And measurement and control are the two most prominent ones I can think of.
Okay. Are there more questions? Yes, Mark Zukoski, please go ahead, Mark. Marek, you can unmute and
No, I
ask
think
your
Marek
question.
made a comment that explains his previous talk.
Oh, it's a comment on this.
Yes, but I can ask you a question, okay?
Okay.
Let's say that was a late answer. I very much enjoyed your talk, and let's say could you comment a little bit of this relation between the coherence theory and measurement? What is your opinion about this flood of papers in which people are considering pre-measurements as measurements?
Well, it's not complete. I mean, I think it's actually it reveals a lot of interesting things, right? If you model a pointer by a single small quantum system and talk about how they can be correlated, I think it's a very interesting thing to do. Yet it does not constitute a measurement.
Okay, very good to hear that we are on the same side, but I'm a little bit more brutal. It isn't a measurement.
Yes, I'm trying to be polite here.
Yes.
And the same thing is, but even the quantum Darwinism or decoherence theory, I like it a lot. But of course, the question is, who is applying these unitaries? I mean, they should basically be done all in an autonomous, natural fashion, right? I mean, it should be the natural interaction between system and environment that leads to those unitaries that lead to the SBS days or the quantum Darwinism or the decoherence theory, which I'm not saying we're the first to say this. Even Zurek mentions this offhandedly, and I guess a lot of other people too. But
and the other thing is that you mentioned that the Hamiltonian should be essentially time independent. Let's say
yes, exactly.
Yeah, I agree, but this is let's say fundamental time independent is when we have everything that we consider is a closed system.
Yes.
Okay. In the case of quantum measurements, let's say even this theory, this decoherence theory, quantum Darwinism, or whatever you call it, you see everything in the context of open. Let's say the subsystems, the important systems are undergoing open system dynamics. Okay?
Yeah, partially, but one should be able to lift it up to a closed system perspective, right? I mean,
yeah, but I think let's say to my intuition tells me then you have to take basically into account the whole universe.
Yeah, because at some point everything interacts with everything else.
Because at certain moment, let's say, any approximation that your environment is governed by only interactions within the environment and perhaps with the system and with the pointer, it's also a kind of putting everything into a closed system box.
Yes, I agree.
Which is very true.
I agree. No, I mean, and here, like, yeah, my biggest problem, and I think this is a problem not of myself only, is considering space-time degrees of freedom. Because if you start thinking about the universe, then suddenly.
Yeah. But I'm very happy that this kind of research is done, and I'm very happy about your result because you have this effective orthogonality, and this is for me enough. I think, let's say, there's a nice phrase in Perez books that you should treat quantum mechanics, this kind of the one that you call textbook quantum mechanics, as just like rules of geometry by Euclid.
Yeah.
And real measurements on Earth are a little bit different.
Yeah, I think we're very much on the same page.
Geometry is not geodesics is not geometry, to put it like that. Okay, so thank you very much. I'm very happy to hear it.
Yeah, thank you very much for the comments.
Any other comments? Any other questions?
Okay, if not,
Marek, one query. What would be your view on those the wave vector reduction models, where you make a stochastic nonlinear correction to
let's say I have only one let's say there are some recent results that there will be some trouble with that because let's say the non-unitarity of this evolution causes some kind of heating.
But the models which do not
but on the other hand, let's say the thing is that, let's say my opinion is like that, and I hope that our speaker agrees with me, is that we discuss quantum mechanics as it is, or we discuss modifications of quantum mechanics, and these are two different topics. Okay?
Yes.
So this lecture was about quantum mechanics as it is, and without any nonlinearities ad hoc in the Schrödinger equation or whatever. And the other thing is modification. So this is a discussion of a different theory.
Agree.
Which may be true, but let's say I wouldn't place my bets on.
Here, I also fully agree. I think we have no reason to conclude that it's not true, but also no indication that it should be true. So I wouldn't bet on it, but it's actually also part of the motivation. I mean, like, to looking at the thermodynamic perspective, we're kind of hoping to uncover maybe some inconsistencies or things, but so far we didn't stumble upon any.
Yeah, but I observed that there are, rather from titles and abstracts, that spontaneous collapse causes some thermal effects.
Yes, there were a couple of really interesting papers that actually showed that if you believe Landau was bound to be true, then you would have infinite heat capacity of every particle in collapse spheres, something like this. I also, just like you, I observed from titles in the abstracts that people say there are some thermodynamic inconsistencies of constant heat production.
No, but also the experiment Donati et al., that Nature paper 2020-21, put some bounds on the heating effect in the underground experiments they performed. So that also we have.
Was it in the context of
that was in the context of the Diosy-Penrose model and also the other some localization models, specific models they referred to. That was the Donati et al. Paper.
I'd say studying small deviations from known laws of physics is very important.
Yes, but they ruled out any such model which have this kind of heating. They looked for the heating effect due to such process. That can occur due to such process. Then a certain class of these models were ruled out, which predicted such heating. So this is a very interesting direction where you start doing experiments, and Baumeister is planning one with the interferometer, mesoscopic mirrors, and so on, to put constraints on such proposed modifications, specific modifications. So in that context, again, perhaps this study of thermodynamics may acquire new relevance and new connotation.
Yeah, so I used the opportunity to say again, thank you for the
Yes,
invitation, the nice
much.
discussion.
Yes.
And I'm sorry, I will not be able to stay logged in today, but I'll look into some of the other talks. But
yes,
I have to pick up my child now.
That. You may look up the program and follow.
Yeah,
this
I will.
reference, and it will be nice to have you with us.